The half-bridge converter is another Buck-derived converter and has its name from those two switches here, which are connected in a half-bridge. The other half of the bridge are the two capacitors over here. In this case, I'm drawing it with the current doubler, formed by the two diodes on the secondary side. The current is doubling as the current from one diode is flowing into that node up here, and the current from the other diode is flowing through that connection to the same node. So the effective output current is twice the current from each diode. We could as well have used a voltage doubler here. We could as well have used a half bridge or a full bridge rectifier. If we would have used a half bridge rectifier or a full bridge rectifier, we could also make that a synchronous rectifier and therefore operate the converter each way from the input to the output or from the output to the input, and therefore make it a so-called bidirectional converter. For now, let's stick to the example of a current doubler. The components on the output here are very similar to what we have seen from the forward converter. And we have a transformer with one primary winding and two identical secondary windings supplying those two diodes. The operation is similar as in the push-pull converter. First, we close one switch, conducting current through that one. Then both of the switches are off, and then we conduct the other switch, and then again both of the switches are off. While we have the first switch closed, the capacitors here form a voltage divider, each of them storing half of the input voltage. That means we have the primary side of the transformer in series with half of the input voltage. The switch up here is a short circuit, and Kirchhoff's voltage law is closed, looking at the input voltage from the DC source. So therefore, we have half of the input voltage across the transformer's primary side. Faraday's law helps us to transform the half of the input voltage to the secondary side, transferred by the turns ratio of the transformer, which is N2 divided by N1. And again, the positive voltage is from the dotted end to the non-dotted end. In terms of Ampere's law, we have current flowing into the dotted end on the primary side, which can escape, which can flow out of the dot on the secondary side, forward biasing the upper diode and magnetizing the inductor, as well as charging the output capacitor and supplying the load, where the return path is the secondary ground here. For the rest of the first half of the period here, both switches are turned off. The low side switch here and the high side switch are off. Nothing is really happening in the transformer here. And the inductor current on the secondary side keeps charging the capacitor and supplying the load and is freewheeling back through the freewheeling diode. And the circuit is closed this way. At half of the period time t, we turn on the other switch, the low side switch here, and conduct current through that one. Now the dotted end of the transformer's primary winding is shorted to the primary ground, which is the negative terminal of the DC supply, and the current returns through the upper capacitor over here to the non-dotted end of the primary winding. We have half of the input voltage in the upper capacitor here, and with the other half of the input voltage across the primary winding from the non-dotted end to the dotted end, Kirchhoff's voltage law ends up with the full input voltage from the DC source. Faraday's law transforms the primary voltage to the secondary voltages with the positive potential at the non-dotted end and the negative potential at the dotted end. So the start of the winding is the one with the dot, and the end of the winding is the one without the dot. Furthermore, half of the input voltage from the primary side gets scaled to half of the input voltage on the secondary side with the turns ratio of the transformer, which is N2 divided by N1. And the same holds for the other secondary winding. Through Ampere's law, we have the current flowing into the non-dotted end on the primary side, escaping out of the non-dotted end on the secondary side through the second diode down here and magnetizing the inductor up here, as well as supplying the capacitor with charges and the output with the load current, and returning through the ground wire to the secondary winding. The other diode here is blocked due to the voltage forced from the upper secondary winding. Finally, the period ends with the freewheeling through the freewheeling diode, forced by the inductor current, which still keeps charging the capacitor and supplying the load, and the return pass is still the ground line on the secondary side. The output to input voltage transfer function, the DC transfer function of the half bridge, is again the duty cycle scaled by the turns ratio of the transformer. For other rectifiers than the current doubler that we have looked into here, you might find other transfer functions, but this is the one as it is shown on the previous slides. And as we have the same control signals that we had for the push-pull converter, so the duty cycle being defined as the on time of one of the transistors, and that is happening twice here, the duty cycle for each transistor is limited to be less than a half of the period. Both of the on times of the switches are followed by the off time of both switches, which is the freewheeling period.